Reality is built on a foundation of breathtaking contradictions. Physicist Niels Bohr found hope in paradox, and by the end of this journey, your entire perception of existence will be fundamentally rewritten. We will venture through 25 cosmic paradoxes that tear apart our conventional understanding of the universe, from the strange rules governing the smallest particles to the immense mysteries at the edge of space. These are not mere puzzles to be solved, but signposts pointing toward a deeper, more profound layer of truth. How can empty space contain more energy than all the stars? And why does the universe appear fine-tuned for life against impossible odds? What does the profound silence from the cosmos truly tell us about our place in it? Are you ready to question everything you thought was real? An empty room is never truly empty. Peer into the void between stars, and you will find a chaotic, seething ocean of energy. Quantum physics reveals that what we call empty space is a temporary stage for a frantic dance of virtual particles, blinking in and out of existence so quickly we can never directly see them. This is the quantum vacuum, and according to our best calculations, it should possess an unimaginable density of energy. The number is so vast it defies comprehension, a 1 followed by 120 zeros. This theoretical energy should be the most dominant force in the cosmos. It should act as a form of anti-gravity, causing the fabric of the universe to expand at such a ferocious speed that no galaxy, no star, no atom could ever hold itself together. Yet, when we look out at the night sky, we see a universe that is, by comparison, remarkably calm and stable. Our cosmological measurements show the actual energy of empty space is almost zero, a whisper against the predicted roar. This is the vacuum catastrophe, a discrepancy of over 120 orders of magnitude, the single worst prediction in the entire history of science. It represents a fundamental collision between our two most successful theories, quantum mechanics and general relativity. One describes the frantic, probabilistic world of the very small, while the other governs the smooth, geometric curvature of the very large. They both work perfectly within their own domains, but when their descriptions of nothingness meet, they produce an answer that is catastrophically wrong. This forces a stunning possibility upon us. Is the universe fine-tuned with a cosmological constant that perfectly cancels out this violent vacuum energy, leaving just the tiny remnant we observe, a value that allows for galaxies and life to form? Or does this glaring error mean we are missing an entire chapter in the book of physics, a deeper theory that reconciles the quantum world with gravity? The vacuum catastrophe is a silent scream from the heart of nothing, telling us that our understanding of reality is profoundly incomplete, and this clash between our theories of the large and the small echoes in another, more personal paradox, one that involves the very nature of light and motion. If every line of sight in an infinite cosmos ended on the surface of a star, the entire night sky would blaze with the brilliance of daylight. This is the essence of Olbers' paradox, a question that troubled astronomers for centuries. Why is the sky dark at all, in a universe assumed to be static, eternal, and uniformly filled with stars? Every direction you looked should eventually land on a star, just as in an impossibly dense forest, every gap between trees is blocked by another trunk. The darkness we take for granted is in fact a profound cosmic clue. The resolution shatters the old idea of a fixed and timeless universe. Our cosmos is not infinite in age. It was born in a fiery beginning roughly 13.8 billion years ago. Because light travels at a finite speed, we can only see the light that has had time to reach us. There exists a cosmic horizon, a limit to the observable universe, and the light from stars beyond that horizon simply has not arrived yet. The sky is dark because the universe has not existed long enough to fill it with light. Adding to this is the relentless expansion of space itself. As light from the most distant galaxies travels across the cosmos, the stretching fabric of space stretches the light waves along with it, shifting their color down the spectrum from visible blue and white to invisible infrared and radio waves. This cosmological redshift effectively steals energy from the light, rendering vast portions of the universe invisible to our eyes. The simple, startling darkness of night is therefore a direct observation of a dynamic, evolving cosmos with a definite beginning. It was a critical piece of evidence that pointed toward the Big Bang. Yet this same expansion that explains the dark sky introduces a far more bizarre and counterintuitive reality, one where the very fabric of space is being torn apart at speeds beyond that of light itself. The very expansion that explains our dark night sky creates another, more profound puzzle, one written in the faint afterglow of creation itself. The cosmic microwave background radiation, a cold whisper of heat left over from the Big Bang, blankets the entire sky. When we map its temperature, we find something deeply strange. No matter which direction we look, this primordial radiation is almost perfectly uniform, varying by less than 1 part in 100,000. This seems logical until you consider the sheer scale of the cosmos. Take 2 points on opposite sides of the observable universe. They are so far apart that light, or any form of information, has not had enough time since the beginning of everything to travel between them. According to the standard laws of physics, these 2 regions have never been in contact. They are like 2 strangers born on opposite sides of a continent that is expanding faster than they can walk, yet they are both wearing the exact same outfit, down to the smallest detail. How could they possibly have coordinated this? This is the horizon problem. Without some form of connection, these distant parts of the cosmos should have evolved independently, developing wildly different temperatures and properties. Their stunning uniformity suggests they were once intimately linked, sharing heat and information as if they were right next to each other. The most compelling solution proposed is a breathtaking event called cosmic inflation. In the first fleeting fraction of a second after the Big Bang, the universe is thought to have undergone a growth spurt of unimaginable ferocity. A subatomic speck of space, already uniform and connected, was stretched exponentially, expanding faster than the speed of light itself. This violent inflation took that tiny, homogeneous patch and blew it up to become our entire observable cosmos. The regions we now see on opposite horizons were once nestled together, close enough to easily equalize their temperature before being violently wrenched apart. Without this inflationary epoch, the cosmic uniformity we observe is a profound mystery, a ghost of a connection that should be impossible. This idea of a primordial super-expansion not only solves the horizon problem, but also plants the seed for the next great cosmic shock, one that concerns the very stuff of reality and the shadowy components that now dominate our universe. That same inflationary epoch which solved the horizon problem also resolves a second, equally baffling feature of our cosmos, its startling geometric flatness. The fabric of the universe can, in theory, be curved. Picture the cosmos as having one of 3 possible shapes. It could be closed like the surface of a sphere where parallel lines eventually meet. It could be open like a saddle where lines diverge forever. Or it could be perfectly flat like a sheet of paper where the rules of Euclidean geometry we learned in school hold true. The fate of the entire universe hinges on which of these geometries is correct. For the universe to be flat, its total density must be exactly equal to a very specific value known as the critical density. This is the razor's edge between a cosmos that eventually collapses back on itself in a fiery big crunch and one that expands forever into an ever-diluting, frigid darkness. The astounding discovery is that our universe is measured to be almost perfectly flat. Its actual density is indistinguishable from this critical value. This seems like a wonderful coincidence until you realize how unstable this balance truly is. Think of trying to balance a pencil perfectly upright on its tip. For a fleeting moment, you might succeed, but the tiniest breath of air, the most minuscule vibration, will send it toppling. Now imagine needing that pencil to remain balanced not for a second, but for over 13 billion years. The initial conditions required for such long-term stability are impossibly, exquisitely precise. Any deviation in the universe's early density, even by 1 part in a million trillion, would have been catastrophically magnified by the relentless expansion. A fraction more density and gravity would have pulled everything back together eons ago. A fraction less and matter would have flown apart so rapidly that not a single star or planet could have ever formed. The fact that we exist to observe a universe that is still expanding at a measurable, stable rate means this perfect balance was achieved. This is the flatness problem. Why is the cosmos so finely tuned? Cosmic inflation provides a powerful and elegant answer. The theory suggests that the violent, exponential stretching of space in the first instance after the Big Bang acted like a universal flattening machine. No matter what the initial curvature of the infant universe was, that incredible inflation would have smoothed it out. Just as blowing up a balloon to an enormous size makes a tiny patch of its surface appear perfectly flat to an ant crawling on it. Inflation forces the universe toward the critical density, producing the geometric flatness we observe today. This is not just a lucky break, it is a direct prediction of the theory. Yet this explanation only deepens the mystery because to achieve this observed flatness, we must account for all the stuff in the universe, and when we add up all the ordinary matter, the stars, galaxies, and planets, we find it accounts for less than 5% of the critical density. The quest to find the remaining 95% leads us directly to the 2 most profound and unsettling mysteries of modern cosmology. Stars on the outer edges of spiral galaxies race around their centers at speeds that defy all logic. Based on the amount of glowing matter we can see, the stars and gas in these vast cosmic whirlpools should be moving much more slowly, like children on a gently spinning merry-go-round. Instead, they are whipping around so fast that the gravitational glue of all the visible stars, gas, and dust should be utterly insufficient to hold them in place. They should be flung off into the void, yet they remain securely bound. Something unseen, wielding immense gravitational force, must be holding these galaxies together. This is the dark matter paradox, a ghostly presence first glimpsed in the 1930s by the sharp-eyed astronomer Fritz Zwicky. He studied the Coma cluster, a massive gathering of galaxies, and found that the individual galaxies were moving so rapidly that the cluster's own gravity should not be able to contain them. He concluded that some form of invisible matter, which he called Dunkelmaterie, must be providing the missing mass. Decades later, the pioneering work of Vera Rubin provided undeniable proof. By meticulously measuring the rotation speeds of stars in spiral galaxies, she found a shocking uniformity. Stars far from the galactic center, in the dim outskirts where visible matter is sparse, were orbiting just as fast as those near the bright core. This flat rotation curve was impossible to explain with the pull of luminous matter alone. It was as if every galaxy was embedded within a giant, massive halo of something we could not see. a cosmic scaffold that provides the gravitational anchor for everything we can see. This dark matter is not a small component. It makes up roughly 27% of the entire mass-energy content of the universe, while all the stars, planets, and nebulae we cherish account for less than 5%. We feel its gravitational influence everywhere, from the way galaxies move within clusters to the way its gravity bends light from distant objects, a phenomenon known as gravitational lensing. Yet, for all its pervasive power, it remains utterly elusive. It does not emit, absorb, or reflect any form of light. It appears to interact only through gravity, passing through ordinary matter and our detectors as if it were not even there. For decades, physicists have hunted for its fundamental particle. The leading candidate was the WIMP, or weakly interacting massive particle, a hypothetical heavyweight that could have been forged in the hot, early universe. But sensitive experiments buried deep underground to shield them from cosmic interference have so far come up empty. Other proposals, like the ultra-light action, continue to be pursued. The stunning implication is that the majority of the matter in the cosmos is made of something fundamentally alien, a substance that does not consist of protons, neutrons, or electrons. It is a shadow universe of matter coexisting with our own, dictating the architecture of the cosmos while remaining forever in the dark. And just as we grapple with this invisible matter, an even more mysterious and dominant force is at work, one that is not pulling the universe together but actively tearing it apart. This accelerating expansion is the work of the most dominant and mysterious force in the cosmos, dark energy. For most of the 20th century, astronomers assumed the universe's expansion was gradually slowing down as the collective gravity of all matter pulled back on the great outward rush of the Big Bang. The ultimate fate seemed clear, a long, slow coast toward either a frozen stillness or a dramatic collapse. Then, in the late 1990s, two independent teams made a discovery that shattered this assumption. By studying the light from incredibly distant stellar explosions known as Type 1, a supernova, which act as cosmic mile markers, they found that these beacons were fainter than expected. Their dimness revealed a shocking truth: the universe is not just expanding, it is accelerating. The galaxies are flying apart from one another at a faster and faster rate. Picture throwing a ball straight up into the sky. You expect it to slow, stop, and fall back to Earth. Now imagine watching that ball instead shoot upward with ever-increasing speed, as if gravity itself had been reversed. This is the baffling reality we now confront. The force driving this cosmic acceleration is what we call dark energy. It is not a substance that clumps like matter, but a property of space itself, a constant energy density that permeates the vacuum. Its effect is one of negative pressure, a sort of anti-gravity that pushes the fabric of the cosmos apart. When Einstein first formulated his equations of general relativity, he introduced a fudge factor, the cosmological constant, to allow for a static universe. He later called it his greatest blunder. It turns out his equations were right all along. Dark energy behaves exactly like that cosmological constant, a uniform energy woven into the very void. The paradox is not just that this energy exists, but its value. Our theories of the quantum world predict a vacuum energy of unimaginable strength, yet the observed strength of dark energy is 120 orders of magnitude weaker. It is a number so infinitesimally small it seems absurdly fine-tuned. If it were any larger, the universe would have been ripped apart before the first stars could ever form. If it were zero, the cosmos would have collapsed long ago. Its precise, tiny value is a riddle that cuts to the core of physics. Furthermore, its dominance now presents a profound cosmic coincidence. Dark energy makes up about 68% of the universe, while dark matter comprises 27% and ordinary matter a mere 5%. Why do we live in this brief sliver of cosmic time where these three components are all significant enough to be observed? For most of cosmic history, matter was dominant, and for most of the future, dark energy will be the near absolute ruler, pushing all other galaxies beyond our cosmic horizon. Our existence in this special moment, this balanced epoch, feels like more than just luck. It suggests we are witnessing a key transitional phase in the life of the universe, a fleeting window where the cosmos is complex enough to give rise to observers who can ponder its own mysteries. The ultimate fate dictated by dark energy is a lonely one, a future where distant galaxies vanish from view, not because they move, but because the space between us expands faster than light can cross it. The cosmos will become an island universe with all other islands lost to an impenetrable darkness. This accelerating expansion, driven by an energy we cannot see or directly touch, is the force that will write the final chapter of everything. And just as this mysterious energy dictates the future of the cosmos, another paradox forces us to question the very nature of our past and our place within it. The serene darkness of our cosmic future, dictated by dark energy, is mirrored by a different kind of darkness, one that presents a crisis at the very heart of physics. Deep within the gravitational grip of a black hole lies a paradox that threatens to unravel our understanding of reality itself. This is the black hole information paradox, a direct war between the two pillars of modern physics. On one side stands quantum mechanics with its sacred, unbreakable rule that information can never be truly destroyed. Think of burning a book. The pages turn to ash and the ink to smoke, a chaotic and seemingly irreversible process. Yet, in principle, if you could track every single particle of ash and wisp of smoke and reverse their motions with impossibly perfect precision, you could reconstruct the entire book, every word and punctuation mark. The information was never lost, just fiendishly difficult to recover. This principle of information preservation is fundamental to the quantum description of our universe. On the other side stands general relativity, which describes black holes as objects of pure geometry, with a one-way boundary called the event horizon. Anything that crosses this point of no return, whether a spaceship, a planet, or a book, is irretrievably lost to the universe. The black hole, according to Einstein's theory, simply gains mass and charge, erasing all details of what fell in. It does not care if it consumed a star or a library. For decades, physicists assumed this was just a strange feature of these extreme objects. Then, in the 1970s, Stephen Hawking made a revolutionary calculation. He discovered that black holes are not entirely black. Due to bizarre quantum effects at the very edge of the event horizon, they slowly leak a faint form of radiation. This Hawking radiation carries away energy, which means the black hole slowly loses mass. Over unimaginable eons, a black hole can evaporate completely, vanishing in a final faint puff of particles. And here lies the catastrophic contradiction. If the black hole evaporates, what happened to the book that fell in? According to general relativity, the information is gone forever, trapped inside and then erased when the black hole disappears. But according to quantum mechanics, that information must still exist somewhere in the universe. Its destruction would violate the core principle of unitarity. The mathematical rule that guarantees the past has a unique connection to the future. We are left with an impossible choice. One of our two most successful theories must be wrong. This paradox is so severe that it forced physicists to propose radical solutions. One possibility is that the information is not lost at all. but is somehow encoded in a deeply scrambled and complex form within the Hawking radiation itself. The final burst of particles from the evaporating black hole would then contain a hidden record of everything it ever consumed. Another, even more mind-bending idea comes from the holographic principle. It suggests that all the information describing the three-dimensional volume inside a black hole is actually stored on its two-dimensional event horizon, like a cosmic fingerprint. The three-dimensional reality we associate with the black hole's interior is merely a projection from the information encoded on its surface. This implies that our own universe, with its rich three-dimensional appearance, might itself be a holographic projection from a distant two-dimensional boundary. The black hole information paradox is more than a technical dispute. It is a fundamental clash of worldviews, forcing us to ask whether space and time, the very stage upon which reality plays out, are themselves emergent properties from a deeper, more information-based foundation. That same profound silence from the cosmos forces a question of a different kind, one not about the fate of information, but about the absence of company. The universe is immeasurably vast and ancient, with billions of Earth-like planets orbiting in the habitable zones of their stars. The raw ingredients for life seem to be commonplace. Statistically, the galaxy should be teeming with civilizations, a bustling metropolis of interstellar cultures. Yet when we listen, we hear only silence. When we look, we see no engineering on a cosmic scale, no visitors, and no signs of anyone else. This crushing quiet is the Fermi Paradox, a puzzle that transforms the cosmos from a potential community into a deeply lonely place. It was famously captured by physicist Enrico Fermi during a casual lunch conversation in the 1950s. If they are out there, he asked, then where is everybody? The question cuts to the core of our place in the universe. Picture a boundless ocean dotted with innumerable islands. Given the sheer number, logic insists that many should be inhabited. Yet from our shoreline, we scan the horizon and see no campfires, no distant sails, no signals at all. The ocean remains empty and still. One of the most unsettling resolutions is the Great Filter hypothesis. This idea suggests that the evolution of life from its origins to a spacefaring civilization requires passing through a series of nearly impossible bottlenecks. There is some stage in this process that is so difficult, so lethal, that almost every world fails. This filter could lie in our past. Perhaps the genesis of life itself from non-living chemistry is a miraculous fluke. Or perhaps the leap from simple single-celled life to complex multicellular organisms is the true barrier. If this is the case, then we are the lucky ones, the first and only to have made it this far. The more terrifying possibility is that the great filter lies in our future. It could be that almost every advanced civilization, upon reaching a certain level of technological prowess, inevitably discovers the means of its own destruction. Whether through nuclear war, engineered pandemics, or a technology we have not yet conceived, they all perish. In this scenario, the silence is a graveyard, and the stars are not a promise but a warning. Other answers are less grim but equally humbling. The vastness of space and time itself may be the answer. Civilizations could be separated by millions of light years and millions of years. They might bloom and fade like fireflies in the night, their brief flashes of glory never overlapping with our own. Or perhaps we are simply not listening correctly. An intelligence millions of years more advanced than ours might not use radio waves, a technology we consider primitive. Their entire existence might be based on physics and communication methods we cannot even perceive. They could be all around us, their artifacts and signals so alien that we mistake them for natural phenomena. another possibility is that they are aware of us and have chosen a policy of non-interference, a cosmic zoo hypothesis where we are the protected, isolated exhibit. The profound implication of the Fermi Paradox is that either answer is staggering. If we are alone, then the entire, unimaginable expanse of the cosmos, with its trillion galaxies, exists for us alone, making life and consciousness the rarest and most precious things in existence. If we are not alone, then the silence is a deliberate and deeply strange condition, suggesting a universe that is either far more dangerous or far more complex than we have dared to dream. Our search for others in the great quiet ultimately reflects back on us, forcing us to confront the nature and fragility of our own conscious awareness. This blurring of reality and illusion finds a chilling echo in the proposition that our entire cosmos might be an elaborate fabrication. The simulation paradox suggests that if any advanced civilization ever gains the ability to run hyper-realistic simulations of conscious beings, then the number of simulated minds would quickly become astronomically larger than the number of original, biological ones. Statistically, any given conscious experience, including our own, would be far more likely to be one of the simulated ones. It is a cosmic numbers game. Think of a master painter who creates a canvas of such breathtaking realism that the figures within it believe they are truly alive, feeling the sun and wind. Now imagine that such artists are common, each producing millions of these living paintings. In that scenario, most conscious experiences in the universe would be artificial. Philosopher Nick Bostrom formalized this unsettling logic, arguing that if such ancestor simulations are possible, then we are almost certainly living inside one. The computational power required is staggering, but not impossible for a civilization millions of years more advanced than our own. They might use the energy of entire stars to power servers that simulate every quark, every neural impulse, every moment of a seemingly historical past. This is not just a science fiction trope, it is a serious philosophical argument that forces us to question the bedrock of existence. If true, the laws of physics we strive to uncover are not fundamental truths, but merely the programmed rules of the simulation, the source code of our reality. Concepts like free will and authenticity become deeply problematic. Are our choices truly our own, or are they the output of a deterministic algorithm running on some unfathomable computer? The paradox is currently untestable, a thought experiment that lives in the realm of metaphysics, yet its power lies in the profound reckoning it demands. We must confront the possibility that the stars we gaze upon, the people we love, and the very memories that define us are not primary realities, but incredibly detailed renderings in a universe-sized video game. This descent into a potentially programmed existence forces us to look even closer at the fundamental building blocks of our world, where the line between the real and the impossible is already dissolving. The power of observation is not merely passive, but a force that can actively shape reality at its most fundamental level. An unstable quantum system, left to its own devices, will inevitably decay like a ticking clock waiting to chime. Yet, if you watch that clock with relentless attention, measuring its state again and again, something astonishing happens. It never chimes. This is the quantum Zeno effect, a phenomenon where the simple act of looking frequently enough can freeze a quantum object in its initial state. Picture an atom poised in an excited, high-energy level. It is eager to release that energy, to jump down to a more stable state and emit a photon of light. But if scientists repeatedly check on that atom, asking it, through precise measurement, if it is still excited, they effectively reset its internal quantum clock. The system never gets the uninterrupted time it needs to evolve and decay. It is like trying to boil a pot of water by only glancing at it every other second. Your constant observation in a quantum sense prevents the water from ever reaching a rolling boil. This bizarre effect takes its name from the ancient Greek philosopher Zeno of Elea, who argued that motion itself is an illusion. In one famous paradox, an arrow in flight must at any single instant be motionless in a specific place. Zeno contended that a series of such frozen instants could never add up to true motion. While our everyday experience clearly refutes this, the quantum Zeno effect shows that in the quantum world, Zeno was onto something profound. Frequent measurements can indeed halt a process, creating a series of frozen quantum instants. This puts the observer in a position of incredible power, directly challenging the classical idea of a universe that ticks along independently, indifferent to whether we are watching. The very act of looking seems to force a definite outcome from a realm of shimmering possibilities. It suggests that reality, at its core, requires a conversation, a relationship between the quantum system and the measurement that defines it. This undeniable influence of the observer leads us to the most famous and debated thought experiment in all of physics, one that takes this quantum weirdness and scales it up to a deeply unsettling and personal level. The unsettling power of the observer, capable of freezing reality through the quantum Zeno effect, culminates in a far more intimate and disturbing scenario. A cat is placed in a sealed box with a diabolical device. A single radioactive atom is linked to a hammer, which will shatter a vial of poison if the atom decays. Radioactive decay is a quintessential quantum process. According to the rules governing the tiny world, that single atom does not have a definite state of decayed or not decayed. It exists in a superposition, a blurred mixture of both possibilities. Since the fate of the cat is tied directly to this quantum event, the entire system inside the box, including the living creature, must also be in a superposition. Until someone lifts the lid and looks inside, the cat is, in a quantum sense, both completely alive and utterly dead. This is Schrödinger's cat, the most famous paradox in all of physics, a thought experiment designed not to be taken literally, but to expose a profound absurdity. The physicist Erwin Schrödinger created this macabre scenario in 1935 as a critique of the prevailing Copenhagen interpretation of quantum mechanics. He was pointing out the sheer strangeness of applying quantum rules to the everyday world. Where do we draw the line? When does the fuzzy cloud of probabilities collapse into a single, definite reality? Is it the moment the Geiger counter clicks? When the hammer falls, or is it only when the information reaches a conscious mind, when a human observer finally peeks into the box and sees the outcome? The paradox forces us to confront the nature of reality itself. Is the universe waiting for us to look at it before it makes up its mind? One radical interpretation seeks to resolve this by accepting all outcomes as equally real. The many worlds interpretation suggests that there is no single collapse. The moment the quantum event happens, the universe splits in two. In one branch, the atom decays, the poison is released, and the cat dies. In the other branch, the atom does not decay and the cat lives on. Both realities are equally valid, unfolding in parallel but forever separate universes. From this perspective, every quantum decision spawns new worlds, creating a vast, branching multiverse where every possibility is played out. The act of opening the box does not kill the cat or save it. It merely reveals which branch of reality you are in. Other theories propose that superposition cannot persist at larger scales. Objective collapse theories suggest that once a system reaches a certain size or complexity, a physical process, not conscious observation, forces it into a definite state. The sheer number of atoms in a cat constantly interacting with their environment might be enough to trigger this spontaneous collapse. ensuring the cat is always definitively alive or dead, even before the box is opened. Yet this only pushes the problem back. What is the precise mass or complexity that triggers this collapse? Is it a single atom, a virus, a cat? The boundary remains infuriatingly vague. Schrödinger's cat ultimately questions the very fabric of existence, forcing us to ask if the solid, predictable world we experience is merely an emergent illusion, built upon a foundation of profound uncertainty. It suggests that the observer is not separate from the experiment but is fundamentally entangled with it, a participant in the creation of reality. And if a single particle and a cat can become so deeply linked, what happens when this quantum connection stretches across the cosmos itself? Einstein's discomfort with a universe built on probability erupted in a powerful challenge to quantum theory, a thought experiment known as the EPR paradox. He, along with colleagues Podolsky and Rosen, sought to prove that the quantum description of reality was fundamentally incomplete. Their argument centered on a phenomenon so bizarre that Einstein himself dubbed it spooky action at a distance. Imagine creating two particles that are intrinsically linked or entangled from the same source. You then separate them, sending one to a lab on Earth and its partner to a distant galaxy. According to quantum mechanics, the properties of these particles, like their spin or polarization, remain undefined, existing in a fuzzy superposition of all possible states. The act of measuring one particle, say, finding it with an upspin, would instantaneously force its distant twin into the corresponding downspin. This influence appears to travel faster than the speed of light, a clear violation of the cosmic speed limit set by Einstein's own theory of relativity. For Einstein, this was unthinkable. He believed in a rational, local universe where objects are only influenced by their immediate surroundings, and no signal could travel faster than light. He insisted there must be hidden variables, predetermined instructions coded into the particles from the moment they were born that would explain their perfect correlation. It was not spooky action, but a hidden plan, like two dice that were secretly loaded to always match before they were ever rolled. For decades, this remained a philosophical debate, a clash of worldviews with no way to test it. Then, in the 1960s, physicist John Bell devised a mathematical theorem that could settle the argument. Bell showed that if hidden variables were real, then the correlations between entangled particles would have to obey a certain limit. Quantum mechanics, with its spooky action, predicted correlations that would break this limit. When experimentalists finally built the apparatus to run the test, the results were unequivocal. The quantum predictions were correct. The particles were correlated in ways that no local hidden variable theory could ever explain. The universe, at its most fundamental level, is non-local. The two entangled particles do not care about the vast emptiness between them. They behave as a single, unified system regardless of the distance. This does not, however, allow for faster-than-light communication. While the correlation is instantaneous, it is also random and uncontrollable. You cannot force the particle on Earth to have a specific spin to send a message to its partner on Mars. The outcome of your measurement is always random, and the person at the other end just sees another random result until they compare notes with you later, at light speed or slower, to discover the perfect match. No usable information is transmitted faster than light, preserving causality and saving Einstein's theory of relativity from collapse, but at the cost of accepting a cosmos where everything is deeply, intimately connected in a way that defies our everyday logic. This quantum entanglement is not a rare curiosity. It is a fundamental feature of our world, woven into the very fabric of the particles that build everything we see and touch. This fluid nature of matter, where barriers can become gateways, finds its ultimate expression in the very origin of the cosmos. How did everything, the totality of the universe, emerge from a state of nothingness? This is the ultimate paradox of existence, a question that seems to defy logic. Nothing, in the strictest philosophical sense, is the complete and total absence of anything, no space, no time, no energy, no quantum fields. Yet here we are, in a universe brimming with galaxies, stars, and life. The resolution lies not in a magical creation, but in a breathtaking consequence of the laws of physics, specifically the wild quantum rules we have just explored. According to the principles of quantum mechanics, empty space is never truly empty. It is a vibrant, fluctuating arena where virtual particles and fields constantly flicker in and out of existence, borrowing energy from the void for fleeting moments. This is the quantum vacuum, and it possesses a fundamental, restless energy. Now combine this with the powerful grip of gravity, as described by general relativity. Gravity uniquely has negative energy. Think of a planet in space. To pull it completely apart, to scatter its pieces to infinity, you would have to add a tremendous amount of energy. Conversely, the gravitational pull that holds the planet together represents a vast reservoir of stored negative energy. In the beginning, the total energy of the universe could have been precisely zero. The positive energy locked in all the mass and radiation we see around us could be perfectly balanced by the negative gravitational energy of the cosmos. From a quantum fluctuation in a primordial nothingness, our entire universe could have simply popped into existence, a colossal bubble of space-time where the positive energy of its contents and the negative energy of its gravitational field cancel each other out exactly. This is not a violation of energy conservation, it is the ultimate free lunch. The universe is the ultimate example of something from nothing, a cosmic sleight of hand where the books balance perfectly. This profound idea suggests that the question, why is there something rather than nothing, might be based on a false premise. Perhaps nothing, in its truest, most unstable form, inevitably gives birth to something. The initial quantum seed, inflated exponentially by a brief period of cosmic inflation, blossomed into the vast and complex cosmos we inhabit today. Our entire reality, in this stunning picture, is a magnificent ripple in the fabric of nothingness. A perfectly smooth, featureless object should hold no secrets and leave no trace. Yet black holes, the simplest objects in the universe according to classical physics, have been caught with a hidden ledger. They possess entropy. This discovery was like finding a fingerprint on a flawless, mirrored sphere, a mark of complexity where none should exist. Entropy is the physicist's measure of disorder, the number of ways a system's internal components can be rearranged without changing its overall appearance. A hot gas has high entropy because its atoms can be in countless different positions, while a perfect crystal has very low entropy. A classical black hole, defined only by its mass, electric charge, and spin, should have virtually zero entropy. It is the ultimate simple object, a cosmic pit that swallows everything and reveals nothing. How could something so simple be so profoundly disordered? The young physicist Jacob Bekenstein made the radical proposal that a black hole's entropy is not proportional to its volume, but to the area of its event horizon. The amount of information or hidden disorder a black hole contains is written on its two-dimensional boundary, not stored within its three-dimensional interior. It was as if the entire contents of a library were not stored on shelves filling the building, but were somehow encoded in the intricate patterns on the surface of its front door. This area law was the first hint of a holographic universe, a breathtaking suggestion that reality might be a projection from a lower dimensional surface. Stephen Hawking initially resisted this idea, but his own calculations then delivered an even greater shock. He proved that black holes are not completely black. Due to quantum effects at the very edge of the event horizon, they emit a faint thermal glow of radiation. A black hole has a temperature. This Hawking radiation directly links these gravitational monsters to the laws of thermodynamics, the science of heat and energy. A hot object with entropy must have an internal structure, a way to store all that hidden information about what it is made of. But here lies the devastating conflict. The classical view of general relativity insists that a black hole is a perfect vacuum, a region of empty, curved space with a singularity at its center. It has no internal parts, no atoms, no molecules, no structure to be disordered. Anything that falls in is obliterated at the singularity, its information seemingly erased from the universe. So how can it have the properties of a complex thermal system? The Bekenstein-Hawking paradox forces a profound choice. Either our understanding of gravity is wrong, or our understanding of quantum information is wrong. The black hole's temperature and entropy are screaming that it is a quantum system with a vast number of microscopic states, a complex repository of data. Yet our classical picture of its smooth, empty interior offers no place for that data to reside. This paradox is the engine that drives the quest for a theory of quantum gravity. It suggests that space and time themselves may be emergent phenomena, arising from a more fundamental network of quantum information relationships. The idea that all the information within a black hole's volume is painted on its horizon is the core of the holographic principle, a concept that could extend to the entire cosmos. Our vivid, three-dimensional reality, with its galaxies, planets, and people, might be a magnificent hologram, a projection from a distant, two-dimensional surface at the edge of the universe. The Bekenstein-Hawking paradox is not a flaw in our theories, but a guiding light, revealing that the thermodynamics of gravity is the key to unlocking a deeper layer of existence, where information is the true currency of reality. This idea that a black hole's entire contents are encoded on its surface was the first breathtaking clue to a far grander possibility. What if our universe itself is a cosmic hologram? The holographic principle proposes that every event and object within any volume of space, from this room to a distant galaxy, is not fundamentally real in three dimensions. Instead, it is a complex projection from information stored on a lower dimensional boundary surrounding that region, much like a three-dimensional image is encoded on the flat, two-dimensional surface of a credit card hologram. Your perception of depth, of solidity, of moving through a world of volume would be an exquisite illusion. The true, fundamental description of reality would be written on a vast, distant surface at the edge of the cosmos, a cosmic film containing the entire script for the universe we experience. This staggering concept emerges directly from the thermodynamics of black holes, where Jacob Bekenstein and Stephen Hawking discovered that a black hole's entropy, its hidden information, is proportional to the area of its event horizon, not the volume within it. The universe seems to be following the same shocking accounting principle. There appears to be a fundamental limit to how much information can be stored in any given region of space, a limit defined by its surface area. This turns our classical intuition completely inside out. In an ordinary storage device like a hard drive, capacity grows with its volume. You add more platters to store more data. But if the holographic principle is correct, the entire information content of the world around you, every atom, every light ray, every thought, could theoretically be encoded on the two-dimensional walls surrounding you. The third dimension, the very space we move through, would not be a fundamental stage but an emergent property, a kind of perceptual output generated by the complex processing of data on that boundary. This provides a radical new framework to finally unite Einstein's theory of gravity with the quantum world. In a holographic universe, gravity is no longer a fundamental force in the same way as the others. It emerges from the same quantum information theory that describes everything else, much like the three-dimensional image of a hologram emerges from the flat, encoded surface. This is a central promise of theories like string theory, where the messy, complicated physics of a gravitational volume can be perfectly translated into a much cleaner, gravity-free quantum theory living on its boundary. The profound implication is a universe of startling simplicity at its core. The endless complexity we see, the dance of galaxies and the flutter of a butterfly's wing, all arise from a vast but fundamentally two-dimensional tapestry of information. Our lived reality, with its rich texture and depth, is a magnificent shadow play, and this compression of all existence into pure information forces us to confront a deeply unsettling question about our own role in the cosmos. If reality is a projection, then what is the nature of the measurement that brings it into focus? That intimate link between observation and reality becomes deeply personal in a thought experiment that places a conscious mind inside the quantum box. A scientist, let us call her Wigner's friend, steps into a sealed laboratory. She performs a standard quantum experiment, perhaps observing whether a single radioactive atom has decayed. She sees a definite result with her own eyes. The Geiger counter has clicked, the atom has decayed. She meticulously records this fact in her notebook. For her, the event is over. The quantum probability wave has collapsed into a single, concrete reality. She walks out and tells her colleague, Eugene Wigner, the result. But Wigner, standing outside the lab, has been thinking. He treats the entire laboratory, including his friend and all its contents, as one giant quantum system. From his perspective, isolated from any measurement, the entire lab remains in a state of superposition. The atom is both decayed and not decayed. His friend, by extension, is in a superposition of having seen the atom decay and having seen it remain stable. She is in a blurred state of having written one result in her notebook and another simultaneously. Who is correct? Both are applying the standard rules of quantum mechanics, yet they have arrived at two contradictory accounts of reality. The friend insists she experienced a single, definite outcome. Wigner insists she is part of a fuzzy cloud of possibilities. This is Wigner's friend, a paradox that pushes the role of the observer to its logical and deeply unsettling extreme. It suggests that the collapse of the wave function is not triggered by a mechanical device, but by the conscious awareness of a sentient being. The friend's consciousness collapsed the reality inside the lab, but for Wigner, that collapse has not happened until he himself interacts with his friend and learns the result. This leads to a dizzying conclusion. There is no single objective reality. Instead, there are only subjective realities tied to individual conscious points of view. The universe fractures into a collection of private perspectives, a form of solipsism where your conscious observation literally creates your world. This seems to shatter the very foundation of science, which is built on the assumption of a shared, objective reality that we can all measure and agree upon. How can we do experiments if the outcome depends on who is looking and when? To escape this, some modern interpretations reframe the problem entirely. Quantum Bayesianism, or Cubism, proposes that the quantum state is not an objective description of a system, but a personal belief, a tool an observer uses to predict the outcomes of their future interactions with the world. For Wigner's friend inside the lab, her quantum state updated the moment she saw the result. for Wigner outside, his quantum state still reflected his own ignorance. There is no conflict because the quantum state is subjective, like a personal betting strategy. The atom itself has a definite state, but our knowledge of it is encoded in these personal, probabilistic tools. Yet, this too leaves a profound question. What is the special property of consciousness that seems to bridge the gap between possibility and actuality? Is there a threshold of awareness that forces the universe to make a choice? The paradox forces us to stare into the mirror, wondering if the mind is not just a passenger in the cosmos, but an active participant in its very construction. This splintering of reality into subjective viewpoints finds a terrifying parallel when we scale the quantum rules up to their ultimate, cosmic consequence. The splintering of reality into subjective viewpoints finds a terrifying parallel when we scale the quantum rules up to their ultimate, cosmic consequence. In a universe destined for a cold, uniform heat death, a state of maximum entropy and disorder, your conscious mind should not exist, yet here you are. The resolution to this contradiction is so bizarre it threatens the very foundation of our cosmic story. If the cosmos is eternal or infinitely old, then random fluctuations in the quantum field should have had more than enough time to create anything, no matter how improbable. And the most probable conscious entity to emerge from the chaos is not a human being with a rich history and a surrounding universe. It is a single, disembodied brain, complete with fabricated memories of a life that never happened, popping into existence for just a moment before dissolving back into the void. This is a Boltzmann brain, and according to pure statistics, you are far more likely to be one of these fleeting phantoms than a person in a coherent 13.8 billion-year-old universe. The paradox arises from the work of physicist Ludwig Boltzmann, who connected the microscopic world of atoms to the large-scale concept of entropy. In a system that has reached total equilibrium, like a room where the air is perfectly mixed, tiny, random fluctuations can still create pockets of order. A brief gust of wind that gathers all the oxygen molecules into one corner is incredibly unlikely, but given infinite time, it will happen. Now apply this to the entire cosmos. Our universe is a stunningly low entropy state, a pocket of exquisite order with complex galaxies, planets, and life. In a cosmos that is eternally old and heading toward maximum disorder, the spontaneous fluctuation that creates a single, self-aware observer is statistically infinitely more likely than the fluctuation that creates an entire ordered cosmos with billions of galaxies. A lone brain is a much simpler, smaller drop of order than the vast ocean of complexity we see around us. So why do we find ourselves embedded in such an improbably grand and structured reality, rather than being solitary minds adrift in a formless void? This is not just a philosophical curiosity. It is a direct challenge to our best models of cosmology. If our universe is just one bubble in an eternally inflating multiverse, where new universes are constantly being born, then over an infinite time frame, the number of Boltzmann brains would utterly swamp the number of ordinary observers like us. We should be overwhelmed by ghosts. The fact that we are not, the fact that we observe a real, coherent, and ancient cosmos, suggests that something is profoundly wrong with the picture of an eternal, inflationary multiverse. Our very existence as beings with a shared past and a consistent environment is evidence that the cosmos is not infinitely old in the way these models suggest. Perhaps the universe had a definite beginning, a low entropy boundary that sets it on a unique trajectory, making our complex reality not a random accident, but a necessary outcome. The Boltzmann brain paradox forces us to confront the eerie fragility of our own memories and experiences. How can you be certain that the world outside your window is not a momentary illusion, a detailed fantasy conjured by a random flicker in the cosmic static. The only answer we have is the staggering consistency of the universe we all share, a consistency that seems to argue against our own statistical improbability. This confrontation with a potentially illusory existence pushes us to question the very fabric of cause and effect, where the future seems to reach back and influence the past as easily as the past dictates the future. Our consistent experience of cause and effect, of memories and aging, rests on a single, baffling fact about the cosmos. Time has a distinct and irreversible direction, an arrow that flies from the past into the future. We take this for granted, but physics reveals this arrow is not a fundamental law. The microscopic equations that govern atoms and forces work perfectly well in reverse. The real source of time's arrow is a cosmic accident, a one-time fluke written into the very first moment of existence. This is the past hypothesis, the paradox that the universe was born in a state of exquisitely low entropy. Entropy is a measure of disorder, and the second law of thermodynamics states that the total entropy of a closed system always increases. This is why ice melts in a warm room, why perfume disperses in the air, and why we remember the past but not the future. These are all one-way processes, driven by the universe's relentless slide from order into disorder. The profound puzzle is why this slide had somewhere to begin. Why did the universe start in such an incredibly ordered state? Imagine a deck of cards coming straight from the factory, perfectly arranged by suit and value. This is a state of very low entropy, a configuration so specific and unlikely that it allows for the entire game of shuffling to take place. Once shuffled, the deck will almost never spontaneously return to its pristine, ordered state. The hot, dense, and remarkably uniform early universe was that perfectly sorted deck. This initial low entropy condition was the wound-up spring that has been unwinding ever since, driving the formation of galaxies, the nuclear fusion in stars, and the intricate chemistry of life. Without this specific starting point, the cosmos would have been a formless, high-entropy soup from the beginning. There would be no consistent arrow of time. Cause and effect would blur. You could see a shattered cup reassemble itself, or feel a memory of tomorrow forming today. The very processes of thought and consciousness rely on this irreversible flow. So why did the Big Bang possess this perfect, improbable order? The question cuts to the heart of cosmology. Some propose that our universe is just one bubble in a vast, eternal multiverse. In an infinite landscape of cosmic bubbles, a few will, by sheer random chance, pop into existence with the low entropy needed for time and life. We simply inhabit one of those rare, lucky ones. Yet this feels like an answer of last resort, pushing the ultimate question into an unseen beyond. The past hypothesis stands as a silent monument to our ignorance, a reminder that the origin of time's arrow is inextricably linked to the origin of the universe itself. This fine-tuning at the beginning, this perfect initial condition, eerily mirrors the precise fine-tuning we find in the fundamental constants of nature. That same initial, perfect order of the universe seems to be written into its very operating code. The fundamental constants of nature are not variable. They are fixed numbers that dictate the strength of gravity, the power of the atomic forces, and the mass of every elementary particle. These values are not predicted by any theory. They are simply measured, and their precise settings are nothing short of miraculous. Think of a cosmic control panel with dozens of unlabeled dials, each governing a different aspect of reality. One dial sets the force of gravity. Turn it just a fraction higher, and stars would burn their nuclear fuel too rapidly, collapsing into black holes before life could ever emerge. Turn it slightly lower, and the gravitational glue would be too weak to pull matter together into stars and galaxies in the first place. Another dial controls the strength of the force that holds atomic nuclei together. If it were even a few % weaker, the only element that would be stable is hydrogen. There would be no carbon, no oxygen, no building blocks for planets or people. If it were slightly stronger, hydrogen would have fused into heavier elements too quickly in the early universe, leaving no long-lived stars to warm orbiting worlds. The cosmological constant, the energy of empty space we encountered earlier, is the most exquisitely tuned of all. Its value is set to an accuracy of 1 part in a number with 120 zeros. If it were minutely larger, the universe would have blown itself apart in a violent inflationary snap. If it were any smaller, the cosmos would have collapsed back on itself almost immediately. Every single dial on this cosmic panel is set to an exact, specific value that allows for atoms, stars, planets, and ultimately, observers. This is the fine-tuning problem, a persistent enigma that suggests our universe is shockingly bio-friendly. How do we explain this incredible fortune? One answer is the anthropic principle. In its simplest form, it states that we observe these specific constants because they are the only ones that allow for our existence. We could not possibly find ourselves in a universe incapable of producing life. It is a tautology, but a powerful one, like a fish marveling that it was born in water. Another, more expansive explanation is the multiverse. If our cosmos is just one bubble in an infinite, eternally inflating meta-universe, then every possible set of physical constants will be realized somewhere in the vast ensemble. We simply inhabit one of the rare, lucky bubbles where the numbers lined up correctly for complexity and life. In this view, there is no fine-tuning, only a cosmic lottery with an immense number of tickets, and we hold the winning one. A third possibility is that these constants are not accidental at all. Perhaps a deeper, underlying theory, a final theory of everything, mandates their values. They are not freely adjustable dials but are locked into place by mathematical necessity, the only possible outcome of a consistent set of physical laws. The search for this ultimate theory, however, brings us to the edge of a final, monumental paradox, a fundamental conflict that has defined modern physics for nearly a century. The smooth, geometric universe of general relativity shatters when it meets the frantic quantum world. We are left with two sets of rules, each spectacularly successful in its own domain, yet fundamentally incompatible when forced to coexist. This is the Unification Paradox, a schism at the very heart of physics. It is like trying to use the precise rules of chess to play a game of checkers on the same board. Both are valid games, but their pieces move in contradictory ways, and trying to combine them only produces nonsense. General relativity gives us a cosmos of smooth, curving spacetime, a continuous fabric where planets and stars glide along gravitational wells. But quantum mechanics reveals a microscopic realm of chance and discontinuity, where particles pop in and out of existence and properties remain fuzzy until measured. These two descriptions cannot both be the final word on reality, because they describe the same universe. Their conflict becomes catastrophic in the most extreme places, like the very center of a black hole or the first searing instance of the Big Bang. In these environments, immense gravitational forces operate at subatomic scales, and our two most powerful theories simply break down, offering only nonsense answers or infinite values. The core of the problem is gravity itself. The other three fundamental forces, the electromagnetic, strong, and weak forces, have all been successfully described by quantum field theory. But gravity, described by Einstein as the curvature of spacetime, stubbornly resists being quantized. We have no quantum particle for gravity, no graviton that we can detect, because the mathematics of smooth spacetime and probabilistic quantum fields violently disagree. To resolve this, physicists have proposed breathtaking new frameworks. String theory suggests that the fundamental constituents of reality are not point-like particles, but incredibly tiny, vibrating loops of energy. The different vibrations of these strings would manifest as all the different particles and forces, including gravity, potentially unifying them under one elegant roof. But this requires extra dimensions of space, curled up into sizes too small for us to perceive. Loop quantum gravity takes a different path, proposing that space itself is not continuous, but is woven from a fabric of tiny, discrete loops, a kind of atomic structure of spacetime itself. This quantum foam would resolve the infinities that plague the center of black holes. Yet for all their intellectual beauty, these theories remain largely untested. They are mathematical marvels in search of an experimental anchor. The elusive goal of a single, overarching theory of everything, one that seamlessly blends the cosmic and the quantum, continues to be the holy grail of physics. This deep division forces a humbling conclusion. Our perception of reality, for all its apparent solidity, is built upon two contradictory pillars. The quest to unify them is not just about tidying up the equations. It is a journey to discover a deeper, more fundamental layer of existence, one where our current concepts of space and time may simply be emergent illusions. At the heart of a black hole, and at the very beginning of time, our equations scream in protest, yielding an answer of infinity. This is the Singularity Paradox, a place where the cosmos writes a check that the laws of physics cannot cash. General relativity predicts that under the immense crush of gravity, matter collapses into a point of infinite density and zero volume, a place where the curvature of spacetime becomes infinite and the very concepts of space and time lose all meaning. An infinity in physics is not a number, it is a glaring error message. It is the universe telling us that our most powerful theory has been pushed beyond its breaking point, like a calculator that flashes an error when you try to divide by zero. These singularities are not just mathematical oddities, they are the ultimate boundaries of our knowledge, hiding the secrets of creation within black holes and at the moment of the Big Bang. Inside a black hole, the singularity is the final destination for anything that crosses the event horizon, a place where the predictable flow of cause and effect is utterly destroyed. At the beginning of the universe, the initial singularity represents a moment when all the mass and energy of the cosmos was contained in an infinitely hot, infinitely dense point. But what does infinite really mean? It suggests a complete and total failure of our description of reality. How can something be infinitely small or infinitely dense? The existence of these points forces a stunning admission upon us. Einstein's magnificent theory of general relativity, which so perfectly describes the orbits of planets and the bending of light, is fundamentally incomplete. It fails to account for the quantum world. At the unimaginable pressures and scales of a singularity, quantum effects must take over. Gravity must have a quantum description, a theory of quantum gravity that smooths out the infinity and reveals what truly happens in these extreme states. Without this theory, we are like cartographers who have drawn a beautiful map of the world, only to find it has a giant, blank region labeled "Here be dragons." The singularity is that dragon, a monster that devours our current understanding. It challenges our deepest held beliefs about determinism, the idea that the past uniquely determines the future. If the laws of physics break down, then anything could emerge from a singularity. Our entire cosmic history, from the first star to your own conscious thoughts, could be the random outcome of a lawless beginning. This paradox is the final, glaring signpost, pointing relentlessly toward a deeper layer of reality where space and time are not the fundamental stage, but emergent properties of a quantum universe we have yet to fully imagine. That symphony you hear echoing through history has no composer, a musical score, a futuristic tool, or a single piece of information can be caught in a causal loop, traveling back in time only to become the very reason for its own existence. This is the Bootstrap Paradox. A composer hears a beautiful symphony, memorizes it, and then travels back in time to meet the young Beethoven. He presents the music to the maestro, who, impressed, publishes it as his own. The composition is passed down through the ages until the composer, in his own youth, hears it for the first time, learns it, and eventually carries it back to Beethoven. Who then created the music? It has no point of origin. It simply exists, an eternal loop where the effect becomes its own cause. This is also called an ontological paradox, a puzzle about the nature of being itself, where an object or idea is passed from the future to the past in a closed, self-consistent loop. It erases the very idea of creation, leaving us with a reality that seems to have written itself into existence. The implications stretch far beyond time travel stories. Some speculative models of our cosmos entertain a similar, breathtaking possibility. In conformal cyclic cosmology, the universe might not have been born from a single, definitive Big Bang. Instead, it could be cyclical, with each iteration, or eon, stretching across trillions of years. In this model, the end of one universe, stretched and faded into a state of maximum smoothness, could provide the precise seed, the initial conditions, for the next Big Bang. The laws and constants that govern our reality would not be set by a mysterious first cause, but would simply be bootstrapped from the previous cycle, a cosmic inheritance with no ultimate beginning. The universe itself would be its own cause, a self-creating loop echoing through eternity. This cyclical nature stands in stark contrast to the standard linear timeline that begins with a singular, explosive moment. It challenges our deepest assumptions about linear causality, where a clear chain of events leads from a definite past to an uncertain future. The Bootstrap Paradox suggests that some threads of reality might be knotted into perfect, self-consistent circles, where the concepts of before and after simply lose their meaning. It forces us to wonder if the very laws we are trying to uncover are not fundamental truths, but merely the stable, repeating patterns of an endless, self-perpetuating cycle. And if reality itself can be a closed loop, what does that say about the nature of the choices we believe we are making? A billiard ball rolling toward a wormhole can become the author of its own destruction. Physicist Joseph Polchinski envisioned a deceptively simple scenario that exposes the raw nerve of time travel. Imagine a wormhole configured as a closed time-like curve, a portal that sends an object not to another place, but directly into its own past. A single billiard ball is shot across a table, on a perfect course to enter this wormhole. It vanishes and instantly reappears a moment earlier in its own timeline, emerging on a trajectory that sends it careening into its own younger self. The collision is perfectly aimed, knocking the earlier ball off its path, preventing it from ever reaching the wormhole in the first place. And here, reality shatters. If the younger ball is knocked away and never enters the wormhole, then the older ball that emerged to cause the collision could never have existed. The entire sequence of events simply vanishes in a puff of logical contradiction. This is Polchinski's paradox, a stark demonstration that the universe's ledger of cause and effect does not tolerate an unpaid debt. The past must be consistent with the future, even when the future invades the past. How can physics resolve such a maddening loop? One compelling answer is that it cannot happen, not because the universe lacks creativity, but because it enforces a law of consistency. The ball would not, in fact, follow a path that creates a contradiction. Perhaps it would only graze its past self, a gentle nudge that alters its trajectory just enough to ensure it still enters the wormhole, but on a slightly different angle, which then ensures the grazing collision occurs exactly as it did. The event becomes a single, self-consistent, and unchangeable loop, like a record groove playing the same notes forever. The ball is both cause and effect, trapped in a dance where its future actions are as fixed as its past. This has a chilling implication for free will. If such time travel were possible, your future would already be written, constraining your present actions to ensure no paradoxes arise. Your choice to enter the wormhole would not be a choice at all, but a predetermined step in a cosmic ballet where you are both the dancer and the choreographer. The laws of physics appear to be robust against such manipulations, either by sculpting events into these stable, consistent loops or, more likely, by fundamentally prohibiting the existence of closed time-like curves altogether. The paradox suggests that causality is not a gentle suggestion, but the universe's ultimate law, a rule so powerful it might bend the fabric of space-time itself to prevent its own violation. Your attempt to rewrite history could be the very reason history unfolds as it does. The Predestination Paradox traps a time traveler in a loop where their actions in the past are not a deviation from the timeline, but the essential ingredient that creates it. Picture traveling back to save a leader from a tragic death. In your rush to intervene, you accidentally jostle the assassin, causing their weapon to fire prematurely and ensuring the fatal shot lands true. Your journey to prevent the event was the very catalyst that guaranteed its occurrence. There is no original, unaltered timeline. The loop is perfectly sealed, a snake eating its own tail. Your future decision to travel was always motivated by the historical record of the assassination, a record that only exists because you traveled back and inadvertently caused it. Every element is locked in place, a cosmic choreography where you are both dancer and director. This paradox annihilates the idea of free will within the loop. Your choices feel real, your intentions pure, but the outcome is fixed. You are an actor reading lines from a script you helped write but cannot remember writing. The universe appears to enforce a brutal consistency where cause and effect are not a linear chain, but a perfect, unbreakable circle. It suggests that if time travel were ever possible, the fabric of reality might be fundamentally rigid, immune to genuine change. The past is not a delicate house of cards waiting to be toppled, but a fortress whose walls are built from the future's own stones. This forces a profound question about our own reality, even without time machines. Is the future truly open and malleable, or are we simply unaware of the fixed tracks upon which we are traveling? Our journey through the labyrinth of cosmic contradictions now leads us to one final, unifying principle, a concept that might weave all these disparate threads into a single, breathtaking tapestry. This final paradox swallows all the others whole. The multiverse proposes that our entire cosmos, with all its galaxies and laws, is just one bubble in an infinite, frothing sea of realities. Every possible variation of physics, every potential history, every choice you did and did not make plays out in a parallel domain. Our universe feels uniquely fine-tuned for life, but in an infinite ensemble, every possible tuning must occur somewhere. We do not live in a miraculously tuned cosmos. We simply inhabit one of the rare bubbles where the numbers allowed for stars, planets, and ultimately, observers like us to arise. It is the ultimate answer to the fine-tuning problem, a cosmic lottery where we hold the winning ticket. Think of a library so vast it contains every book that could ever be written, including every possible variation of every story. Most of the books are gibberish filled with random letters. A few contain a coherent sentence. Far fewer tell a compelling story. Our universe is simply one of those rare, readable volumes on an endless shelf. This breathtaking idea emerges naturally from our most ambitious physical theories. Eternal inflation suggests that the rapid expansion of the early universe never truly stopped, but continues eternally in a background meta-universe, constantly spawning new bubble universes with random physical properties. String theory's landscape posits a staggering number of possible stable configurations for the extra dimensions it requires, perhaps 10 to the 500 different versions, each corresponding to a universe with its own unique laws. Even the many worlds interpretation of quantum mechanics creates a new universe with every quantum decision, branching reality into a limitless tree of possibilities. The paradox is not the existence of these other worlds, but what their existence means for science itself. To be considered scientific, a theory must be testable and falsifiable. It must make predictions that can, in principle, be proven wrong by observation or experiment. But how do we test for a universe that is, by its very definition, beyond our causal horizon, forever separated from us by an unbridgeable expanse of inflating space? Any evidence we could possibly gather is confined to our single bubble. The multiverse, for all its explanatory power, risks becoming a metaphysical concept, a beautiful story that can explain everything but predicts nothing specific about our own reality. It offers breathtaking answers at the cost of moving the ultimate questions into an unseen and unseeable beyond. Is this the final, elegant resolution to the cosmic coincidences that have haunted us? Or is it the ultimate evasion, a retreat from the search for a unique, fundamental theory of our one and only universe? The Multiverse Paradox leaves us standing at the edge of knowledge, staring into an infinite reflection, forced to wonder if the ultimate nature of reality is forever beyond our grasp. These paradoxes are not dead ends, but signposts pointing toward a deeper truth. Each one emerges at the very limits of our understanding, a place where our most brilliant theories crack and strain under the weight of new evidence. They are the growing pains of a science that is not failing, but succeeding, pushing beyond comfortable illusions into a more profound and startling reality. This journey through cosmic contradictions is a masterclass in humility. It teaches us that our common sense, built in a world of medium-sized objects moving at slow speeds, is a hopeless guide for navigating the quantum froth or the stretched fabric of the cosmos. The universe was under no obligation to be intuitive, and these paradoxes are its way of reminding us of that fact. From the spooky connection of entangled particles to the silent scream of the vacuum catastrophe, these puzzles force us to dismantle our most basic assumptions. What is real? What is time? Are we separate from the universe we observe, or are we participants in its very creation? The answers, when they finally come, will not be a simple list of facts. They will reveal a unified reality where the observer and the observed are entangled, where the finite and the infinite coexist, and where the past and future may be as interwoven as the threads of a tapestry. The pursuit of these mysteries, this relentless questioning in the face of the unknown, is the very engine of discovery. It is what transforms the map of reality from a simple sketch into a living, breathing, and infinitely complex masterpiece. These 25 cosmic paradoxes have torn at the fabric of everything we thought was real, from the vacuum's violent hidden energy to the unnerving possibility of a simulated existence. Each one of these contradictions serves as a brilliant beacon, a signal flare illuminating the absolute limits of our current knowledge and guiding our search for a more profound, unified theory of everything. The biologist J.B.S. Haldane offered a perfect summary of our journey when he said, "The universe is not only queerer than we suppose, but queerer than we can suppose." Our own imagination, bound by the rules of this reality, may be fundamentally incapable of grasping the full, unvarnished truth. Let this exploration be a starting point for your own boundless curiosity. Carry these ideas with you, reflect on them in quiet moments, discuss them with friends, and never stop questioning the very nature of the world around you. The greatest paradox of all may be this: the more we learn about the cosmos, the more we are humbled by the vast, uncharted ocean of what we have yet to discover. Every answer simply peels back another layer, revealing a deeper, more magnificent mystery beneath. If this journey has expanded your perception of reality, consider subscribing for more deep dives into the secrets of the cosmos. We would love to hear which paradox bent your mind the most, so share your thoughts in the comments below.